So I got this calendar for Christmas, or New Year's, I guess, and it's a beautiful calendar. And I thought, well, this is like kind of like a word of the day kind of thing, right? Maybe I'll learn about these elements, right? I've forgotten all about them, right? High school maybe was the last time I really ever dealt with elements, but I started looking at them, and I tell you, I think there's some cool stuff hidden in here. So let's do a quick deep dive into elements, right? So how we see here, boron, carbon, nitrogen, oxygen, right? This concept that we kind of came to Earth and started building it. Let's take that perspective, right? And you can see they've given us some information about how a lot of this is constructed. You can see helium. Number 2, atomic weight is 4, and its electrons. Looks like there's 2, right? So 2, 2, 2. So maybe we skip ahead to August, right? This is a good one, right? 6, atomic weight 12, electrons 6p. So before we go any further, let's make sure we all kind of understand what those numbers mean. And so over here, I'm just going to list those first, just the first 6, right? We're not going to need to go. I think I can make a point at 6, I think. So let's just look at hydrogen, helium, lithium, beryllium. What's beryllium? Is Be, right? Boron and carbon. What are all these? And they're the first 6. So if we look at like for boron's a 5, right? Carbon's a 6. So what does that mean? So if you do a little research, right? Search again, research, just to make sure, you realize that there's these things called electrons. And then that's got like a negative charge to it. And then there's a proton, and that's got a positive charge to it. And in between those two, I imagine, is something called a neutron, which doesn't have a charge to it, but it has weight, right? And I don't think the electrons have weight, but the electrons and the protons both exist together, so they have weight. So if we just look at these as 3 columns, we can see the hydrogen, right, has 1, and that means it has to have a proton, and then it has almost a whole neutron, so we'll just give it 1. Helium, it has 2, right? We just kind of looked at helium, 2, and then the atomic weight is 4, so you subtract these 2 to get the neutrons, right? So there's 2, and if there's 2 electrons, right, then there's 2. Lithium, that's cool. I believe that's 3, 3, 3. Beryllium, we're going to give 4, 4, 4. I think if you look at this one, this 4, maybe the neutron is closer to a 5. But for this example, this is a rough order of magnitude here. Right? Now, boron, you can see here, is a 5. Right? So it's got 5 of those. And if you look, it does have 10 as its atomic weight. So we know that it's 5, 5, 5. And then carbon, 6, we look at that, 6, 12, 6 paired electrons. So its electrons are 6, its neutrons are 6, and its protons are 6. So that's a cool way of looking at the first 6 elements on the periodic table and what the numbers mean. And so now maybe we can discuss why we have 3. Like, is this granularity? Could we maybe just cross off and just say, let's imagine that there is no such thing as an electron, a neutron, and a proton. Instead, let's imagine it like we'll come up with a new word that encompasses all of those. And because we're going to come up with a new word, and since these are all the same, we're just going to cross off the 2 of each. So we're going to be left with just the single number. Right? Just simplify it down. Like, why all the 2s and all the 3s? Like, I get the point. I can double it. Let's look at these now as just these elements. I'm going to put them over here. And the new thing we're going to come up with, right? So we're trying to figure out, like, what's an electron, a neutron, and a proton, right? What is this charge? All right, let's dive a little bit deeper and see if we can find some cool stuff. So let's imagine you're building Earth. I don't know. You're making these. We're going to build these out of these things, right? These little blocks, bumping particles, we could say. But they don't really exist, so we're going to come up with a different. So there's only three forces in the whole universe, right? And I know this for a fact. Three forces. The first one's called dielectricity, right? Dielectricity. I guess you could say the ether, right? This rarefied gas that exists in between all things, even up in space and down on Earth, but everything's kind of this one fundamental source of dielectricity, right? This exists in counter space. All right, so you can even think of dielectricity as this invisible potential in counter space, right? The second force of the universe is magnetism. So magnetism is kind of like this ability to displace the dielectricity. If you can imagine a magnet and you look at it through some sort of viewing film, or you're looking at this magnet under some ferrofluid, right? You can start to see the dielectric lines. You can see these kind of lines of force start to develop because of the magnet, right? The dielectric field, you can't see them if you just hold the ferrofluid up, but you interact it with a magnet, and you can start to see these things. So then, what's the third, right? The third force of the universe is geometry, right? Let's look at geometry. Let's look at geometry and just say, okay, give me some geometry of dielectricity and magnetism. Right? Let's look at in its simplest form, if we show you dielectricity and magnetism, right? Or how we can interact those two fundamental primordial forces to create something really cool, right? So imagine dielectricity as the plane of inertia, right? Inertia or acceleration, right? Inertia and acceleration. This is the plane of dielectricity, right? And then using geometry, we are going to conjugate this with magnetism, right? So this is force and motion, right? So when we hook dielectricity and magnetism in this way, we end up with something really cool, right? It's called like the toroid, and I believe it goes like this kind of thing, right? And then there's another one that's going this way, and so you end up with this beautiful, right? You kind of got a hyperbole and a toroid, right? If you can imagine, this starts to, right? And this is the blotched wall. You can see this acceleration here. This is the blotched wall of inertia and acceleration, and then this force and motion. You can see these dielectric lines of force. If you were to look at, ferrofluid or some sort of magnetic, you can actually see, right? This just, and then here it kind of looks like a bulge, right? And everything's kind of moving in this beautiful pattern, right? So this is kind of at its simplest how we would interact something, say, from counter space, like one dielectric line of force, and we were to put it into space, right? What could we produce? What kind of shapes could we produce? And do these shapes have any clues that can kind of give us some information on kind of how the ether is formed, how the elements are formed? There was a great book. You remember, these elements were all coming out of like the 17 and 1800s, right? A lot of this electricity, motors, these concepts were coming out of the, steam engines, 1800s. So these concepts, Walter Russell did a great book called The New Concept of the Universe, I think, where this is in the 20s, late 20s maybe, and he produced a kind of a new concept of the periodic table. And so I think that maybe this will kind of fall into that a little bit. But so here's the idea. So we want to build the first, right, hydrogen. Forget about electrons, protons, neutrons. I like the charges, right? So let's just say that we have this special tool, right? And here it is. I bought this on the internet. It's a special tool. You see the tip, and it's designed, right? It allows me to grab one dielectric line of force and terminate it, right? It allows me to do that one at a time. So because hydrogen has one dielectric line, let's start with that. So out we bring this dielectric line. It terminates, right? And it's about that long, right? So going this way is counter space, and we've just taken it out of counter space and put it into space. So if you want to still keep on the electron idea, imagine that this is the node that makes contact, right? We'll call that the electron. And then counter space is providing us that positive, so we can call that the proton. And then the actual line, we're going to call that kind of the neutral zone, right? So that's kind of this dielectric line, right? We could imagine, if we were to now try to capture this, right? So we bring one into existence, and poof, it disappears. You go, whoa, where did it go? So you put a fishbowl, right? So we'll put a fishbowl over it, right? And you bring one dielectric line, and you place it in the fishbowl, and it just sits there. You go, oh, look at that. What is it? Remember, let's say that's negative, and that's positive. Counter space, we've brought it from counter space into space, and now it's going to start to chooch like a little motor, right? This is the idea. It's now doing this little orbital. We've basically made a circuit from counter space into space. Now it exists as matter, right? But it's hydrogen. We got to capture these things because they just float away, right? They float away. So let's just send like a half dozen up in there, and let's watch what happens, right? So we send about a half dozen of these, and they kind of self-organize, right? Maybe we've seen this somewhere else where we're going to, kind of self-organize it, right? So we send a whole bunch, right? There's 3, and we go, you know what, we're going to send another one, and another one, and another one. Now we got 6 up there. 1, 2, 3, 4, 5, 6. We go, oh, wow, they kind of made this cool shape, right? What is that shape that they made? Let's see if I can draw a better version of that, right? What kind of shape is it? So they kind of self-organize like this, right? You go, oh, look at that. Each dielectric line of force connected to the one next to it, and they formed this beautiful hexagon, right? And then we throw some more up there, and they start to connect up in these ways, and you go, oh, look at this. We're forming this idea of a hexagon. So this is kind of gets into principles of crystals, right? This is kind of like the crystalline, analyzing them on a crystalline form, and you go, this crystal here is hydrogen. This is so cool, right? We take the fishbowl off, it floats away, right? So we could say, oh, cool, this is neat. We could say that this hydrogen forms, right, self-organizes into these cool shapes, right? That kind of exist like this, and they're going to call those just hexagons or hexagonal, right? It's a hexagonal molecule, hexagonal, hex, O-G-O-N-A-L, right? Hexagonal, right? So we'll say that this is a hexagonal molecule, atoms, right? Whatever you want to call it. So moving on, we say, that was fun. We brought one dielectric line of force into existence, and we received hydrogen, and it formed the hexagons. This is cool. Let's move on to the next one. I'm going to now bring, learning maybe from the last one, I'm going to put a fishbowl up here again. I'm going to bring 1, and then a 2, right? There's two dielectric lines of force, and they hook together, and you go, okay, what do I have here? Right? This is now two dielectric lines of force brought into existence, right? And this is helium, right? Helium has two, right? So you could say there it's two, right? But its counter space equivalent is there, positive, right? Right? And this is the, so as you can see how now this, right? This kind of forms two little motors. You go, holy cow, look at this. This is helium, right? Let's throw some more in there, right? Let's get a whole bunch. Let's get a whole bunch in there. So we realize that this is now, instead of this one little motor chooching around, we kind of get this concept that there's this double motor, which actually looks like three orbs, right? You can imagine it looks like three orbs, right, as these potentials move. So what happens if we throw a whole bunch in there, right? So we start to throw a whole bunch in there. And very similarly, these things start to self-organize. Let's say we just keep pumping them in there, and they start to self-organize. Only this time, right, we start to see, because each one of these, boom, they start to form very similar, this hexagon, right? We start to see now an interesting transition, right? They start to organize and form, right, what's called a hexagonal close packed, right? Or we'll call it just a hexagonal close pack, right? Totally different, right? This hydrogen individual, this is now forming, let's look at this motor, right? And just imagine that each one of these is its own little orbiting, right? And then this one's also going to go orbiting with this one, right? And this one's going to be orbiting with this one, right? And this one's orbiting with this one, right? Because we got these potentials. Remember the potentials? Look at the positive and negative potential. So you can see what starts to develop here when we start to, everybody's orbiting, right? It's this orbital, right? Now there's the concept that we're gonna pack these in, looking at them like spheres. Now at this point, you could probably just start to Google this type of hexagonal close pack and see how it just continues underneath here. We could put 4, and then below that we put, right? And we could just keep packing these infinitely this way, whereas, right, hydrogen was kind of going this way, right? Single flakes. These are all kind of grouping together, right? Because of these little motors. So this idea, well, we're just going to say it forms a hexagon, right? But it's a different type. Now we're getting into crystalline lattices, right? From just single crystal formations to now this ability to create a lattice, right? This ability to create a grid, right? Or a lattice, right? So this, now, here's where it gets really cool, right? We talk about the next one, lithium, right? So we've taken now one dielectric line of force, put in existence, they self-organized into a hexagon. And then we brought two dielectric lines of force in together, and they started to form helium, which was this same kind of hexagonal, but it was close packed, right? So then we go lithium. Let's get crazy. Here comes 3, right? Maybe we put up our fishbowl just in case, right? So we bring 3 dielectric lines of force together. And what do you know? They hook, right? Right? Imagine these little motors, plus, minus, right? Plus, minus, right? And so we got a little choocher like this, right? And then this little choocher like this. So we got this cool lithium, right? Which has got 3 and splat right to the ground. You go, holy cow, look at that, right? This is now our first alkaline metal, right? We put 3 dielectric lines for. We send a bunch of them into there. Let's keep adding to this pile, right? And these self-organize into kind of a different pattern, right? These start to self-organize into this pattern, right? So we get a whole bunch of them in a room together, and they self-organize into something like this, right? You get these. So now imagine each one of these points are now going to fold inward, right, and form a pyramid, right? But, right, this is just kind of it laying out, right? If you were to imagine all these points fold in on the point, so you end up with this four-pointed, right? If you were to look at it from the top, like the Great Pyramid of Giza, you end up with a four-sided pyramid, right? And so lithium, right, 3 dielectric lines of force, we bring them in, we put a bunch of them together, and they start to self-organize into what's called a BFC, right? So or a body-faced cubic, right? So it's definitely a cube. If we were to imagine this is drawn into, right, a 3-dimensional cube, right? And each square here is a base of the pyramid. So you can see this one folding in, then this base on this side is folding in, and then you've got one here, one at the bottom, and then forget, you got one in the front and one in the back, right? So there's 6 of these pyramids all folded in on each other to create a what's called body-faced cubic, right? So that's pretty cool, right? We've got now 1 turns into hexagons, 2 of them turns into these hexagons that are tightly packed together or close packed, right? We get 3 dielectric lines of force to create the 3rd, right? And we get lithium